Module 11.1. As a reminder, it is recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 11.1. Now that we know how to collect sample data and how to describe the data, how can we use it to learn about the population? In previous modules, we discussed how to collect sample data and how to summarize data. In this module, we will look at how to take the information contained in a sample to learn about a population. In many situations, the aim of a study is to learn about a population of interest. Unfortunately, collecting data from every element in a population can be difficult. Instead, researchers will take a subgroup from the population known as the sample to examine. Please take a moment and review these definitions. In this module, we're going to begin to develop a set of tools that will allow us to take the information contained in the sample to say something reasonable about what is occurring in the population. We will accomplish this by studying the behavior of the statistic and then see what the behavior of the statistic suggests about the parameter. Notice that the parameter is the information we really want, but usually only get to observe the statistic. It is vital at this point to emphasize that the vocabulary and notation are essential for the course. Make sure to keep track of definitions and ideas. Previously, we already saw notation for different types of statistics and parameters. Values calculated from sample data are statistics, and values calculated from population data are parameters. We can summarize the information in a table. Looking across the rows, we notice that each statistic has a corresponding parameter and vice versa. For example, looking at proportion, we can see that p hat and p are a pair. From this point forward, we can think of each statistic as being paired with the corresponding parameter. We are going to learn how to use the value of a statistic to say something reasonable about the corresponding parameter. Most of the time, we cannot collect population data, and since the parameters are calculated from population data, we cannot calculate parameters directly. In cases where population data cannot be collected, we can only learn about parameters via the statistic, which we can calculate. Previously, we defined statistical inference as the process of using the information contained in a sample to draw conclusions about what is happening in the population. Now we can be even more specific. We can think of statistical inference as the process of drawing conclusions about the unknown parameter based on the calculated statistic. Notice when we say unknown parameter, we mean that the value of the parameter is unknown. Carefully read each of the scenarios and identify the parameter in the statistic. For each scenario, give the notation and the value if the value is known. The first is solved for you. The Fayette County Health Department Public Health Clinic is interested in what percentage of appointments during the 2021 year were canceled without being rescheduled. Looking at all of the appointments made during 2021, 15% were canceled without being rescheduled. A random sample of 200 appointments was selected, and out of the sample, 17% were canceled without being rescheduled. The population is all of the appointments made in 2021. Therefore, the parameter is the percentage of all appointments that were canceled and not rescheduled. The appropriate notation and value are p equal to 0.15. The sample is the selected 200 appointments. The statistic is 0.17, the proportion of sampled appointments that were canceled without being rescheduled. The appropriate notation and value are p hat equal to 0.17. Try the next two on your own, and then come back to the video for the solutions. A recent news article claims that 1 in 20 teens have diagnosed anxiety or depression. The population is all U.S. teens, therefore the parameter is the proportion of all U.S. teens who have diagnosed anxiety or depression. The appropriate notation is p, and the value is unknown. The sample consists of teens surveyed by the news article. Therefore the statistic is 1 out of 20, or 0.05. The appropriate notation and value are p hat equal to 0.05. A nutritionist wants to estimate the mean amount of sodium consumed by children under the age of 10. From a random sample of 75 children under the age of 10, the nutritionist obtains a sample mean of 2,993 milligrams of sodium consumed. The population is all children under the age of 10. Therefore, the parameter is the mean amount of sodium consumed by children under the age of 10 per day. The appropriate notation is mu, and the value is unknown. The sample consists of 75 children sampled. Therefore, the statistic is 2,993 milligrams. The appropriate notation and value are x bar equal to 2,993 milligrams. Do we know anything about the behavior of statistics from random samples? If we are going to use statistics to learn about parameters, we need an understanding of how statistics behave. Previously, we discussed random samples. It ends up that if we select the sample randomly, we can say a lot about the behavior of the statistic. To illustrate how the statistic behaves, we will start with an example where we have access to population data. We will be looking at the winning race times for the Kentucky Derby since 1875. First, we will summarize the population data. We will start with a dot plot of the population data. The mean winning time is mu is equal to 129.28 seconds with a standard deviation of sigma equal to 12.71 seconds. Also notice that the distribution of the population data is right-skewed and bimodal. Next, we will take a random sample of 30 race times and look at the plot of the sample data. The mean winning time is x bar equal to 131.51 seconds with a standard deviation of s equal to 14.89 seconds. Also notice the distribution of the sample data is right-skewed and the overall shape is similar to the shape of the population distribution. Next, we will take a second random sample of 30 race times and look at a plot of the data from the second sample. The mean winning time is x bar equal to 130.38 seconds with a standard deviation of s equal to 14.41 seconds. Again, the distribution of the sample data is right-skewed and the overall shape is similar to the population distribution. We can see that when we take random samples from the population data, we typically end up with sample data that is similar in characteristics to the population data. Our goal is to learn about the behavior of the statistic. For this example, the statistic we are interested in is x bar. Notice the value of x bar was not the same for each of the samples. In the first sample, x bar was equal to 131.51, and in the second sample, 130.38. Further, neither statistic was exactly equal to the parameter, mu, but all values were close to one another. Definitions. Sampling variability is the change in the value of the statistic from sample to sample. Sampling error occurs when the statistic is not equal to the parameter due to looking at a sample instead of a population. Next, we are going to continue the process of taking samples from the population and calculating the statistic from each sample. This will need to be repeated many times. We will look at 5,000 samples. Looking at the diagram, we have the population of all Kentucky Derby winners. We're taking 5,000 different samples, and from each of those samples calculating the sample mean x bar. Notice that we have a long list of statistics. We note the value of the statistic will vary from sample to sample. The parameter does not change from sample to sample. It is a fixed value. In this case, mu is equal to 129.28. We can visualize the statistic calculated from the 5,000 samples by plotting them in a dot plot. Notice that the plot of the 5,000 statistics is symmetric and bell-shaped. Also notice that the plot is centered at 129.28, the value of the parameter. This plot helps us visualize what is known as the sampling distribution. A sampling distribution is the distribution of a sample statistic computed from different random samples of the same size from the same population. A sampling distribution consists of all possible statistics and how often these statistics occur. It helps us visualize how the sample statistic varies from sample to sample. The above simulated sampling distribution was created as a dot plot. We could have just as easily created a histogram. When a distribution is bell-shaped, unimodal, and symmetric, with the mean, the median, and the mode at the center of the peak, we often say the data comes from a normal distribution. Properties of the sampling distribution. Center. If the samples are randomly selected, the sampling distribution is centered at the population parameter. Shape. For many common statistics, the sampling distribution will be symmetric, unimodal, and bell-shaped if the sample is large enough. In other words, many statistics are normally distributed if the sample is large enough. There are other possibilities such as t-distributions, f-distributions, and chi-squared distributions. We will look at these in later modules. Note that if you take random samples, the sampling distribution will be centered over the actual population parameter. If bias exists, in other words, you do not take random samples, your sampling distribution may give you the wrong information about the parameter, and it may not be centered at the value of the parameter. Remember, we are trying to understand how the statistic behaves from sample to sample. We can summarize the behavior similarly to how we would summarize data in previous modules. The sampling distribution is a plot of the statistics and provides a visual summary. Numerical summaries are also useful. We can look at the mean of the statistics and the standard deviation of the statistics. The standard deviation of the statistics is very important because it will help us assess the uncertainty of the statistic in estimating the parameter. In other words, it helps us describe how the statistic changes from sample to sample. The variability of the sample statistic is so important it gets its own name. The standard error of a statistic is equal to the standard deviation of the statistic. The standard error measures how much the statistic varies from sample to sample. The standard deviation of the sampling distribution is equal to the standard error. As the sample size increases, the standard deviation of the statistic tends to decrease, and the statistics tend to be close to the true value of the population parameter. Therefore, small sample sizes will produce a sampling distribution with large standard error, and large sample sizes will produce a sampling distribution with small standard error. In the worksheets for this module, you will build a sampling distribution. There is a fundamental theorem in statistics that informs us that the sampling distribution for the statistics given in this table will be normally distributed under certain conditions. The central limit theorem can be applied to describe the behavior of each of the above statistics when repeated random sampling is performed. Next, we will look at the central limit theorem for each of these statistics. First, we have the central limit theorem for a single proportion. Notice here we have that the mean is equal to the population proportion p. We have the formula for the standard error, and we know that the shape of the sampling distribution, if the sample size is sufficiently large, will be reasonably normal. In order for this to hold true, we need the following sample size requirement. We need n times p to be greater than or equal to 10, and n times 1 minus p to be greater than or equal to 10. Also located in the video script are the central limit theorem for a single mean, a difference in proportions, and a difference in means. Please read these on your own. One of the most important parts of the central limit theorem is the sample size requirements. The sample size requirements given above are general guidelines. Other resources may use slightly different requirements. To predict the behavior of the statistic, we need the sample size to be reasonably large. Many people think that a sample needs to contain hundreds of thousands of people before we can make valid inference. Notice that the required sample sizes are much smaller.